Hello and welcome to section 18. In this section we're going to be going over sinusoidal signals and how to model them eventually as exponential signals. This video specifically will be going over just how sinusoidals are made, what they look like, and how to evaluate them. So you can see at the top here we have our motor. It spins some magnets, there's some coils, and we produce, so this will be called three-phase AC, because there's three different phases of AC current. So a sinusoidal signal looks like this. So let's focus on this curve here. So if I highlight it from here to here, so where it crosses the zero to where it crosses the zero, that is considered to be one cycle. That would be equal to one cycle of that motor up there, or what we're going to call a one period. So that is capital T. Each of these, so there's also this other curve here, this green one. So if I highlight it from when it crosses zero to when it crosses zero, that is also one period. It's this actually the same period, they're just in different phases. We can calculate the phase difference. Let me see if I can get a different color here. By looking at the difference. So for instance, this one starts here and rises, and then sometime later this one will start and rise. The start of this one's rise corresponds with basically the peak of this one. So what I can tell you is that means that these are roughly 90 degrees out of phase. If they were 180 degrees out of phase, what you would see is the green one would go up and down, and the red one would be inverted. So that would be 180 degrees out of phase, because this point for the green one is equal to this point for the red one, and then this time right here, small t, if we take that small t and we divide it by big T, which is our period, that'll tell us how much out of phase we are. Alright, so other things we want to know about, there's this peak-to-peak voltage. Generally, your peak-to-peak voltage is double your magnitude. The form of our equation is right here. So we're going to get some magnitude. So magnitude means how far above the zero are we. So as long as it's centered, then our magnitude will be equal to half our peak-to-peak. But there are cases where we can shift this up or down by adding in some DC voltage or current. Then we're going to have a sine function. You can also have a cosine function. We're going to more often we're going to have a cosine function. Omega t plus phi. So the omega term, that's how fast this motor up here is spinning. So the faster that motor spins, the faster the cycles, the shorter our period is. And then phi is that phase shift that I showed you how to calculate. And you can do that in degrees or in radians. A lot of times it's written in degrees. Alright. So let's go over to the visualizer and just kind of rewrite what we have there. So this is example 1. Example 1 asks us to write v of t equals 1 cosine 0.1 t minus 30 degrees at t equal to 1 second. So we want to know what the voltage is. By the way, this also works for current. It doesn't have to be a cosine, but most of the time the functions you're going to see in the homework are a cosine function. So this takes the standard form. So the standard form is v of t equal to v magnitude, cosine or sine. Again, most of the time we're going to see cosine, times omega t plus phi. So what we can see here is we have a magnitude of 1. Our omega is 0.1 radians per second. So it's about, if you convert 0.1 radians per second to RPM, you're going to have about 1 revolution per minute. And then we are 30 degrees out of phase. And it's in the negative direction, which means that we are ahead. So we're to the left 30 degrees. Omega isn't always useful to use, so some other equations. And so these are just some generic equations that go in those boxes that you saw on the handout. omega can be rewritten in terms of other things. So one full cycle around that for the motor is 2 pi. The period corresponds to that. So if I take that 2 pi and divide it by t, how long does it take it to go over that 2 pi rotation? That is omega. So remember, this t here is the period that we define on that graph above. This is angular velocity or angular frequency, whatever you want to think of it as. Think of it as like how fast the motor's spinning. That's producing this AC current. And then I can also rewrite this as 2 pi times frequency, because frequency is equal to 1 over t. And you can also say t is equal to 1 over frequency. So if I say something is, say, 1 kilohertz, well, 1 kilohertz is equal to 1 over t seconds. So that means t would be equal to 1 divided by 1k, which would be 1 millisecond. So if you ever needed to convert from hertz to seconds, that's how you would do that. All right. So what we want to do, so let's bring this back down. We want to evaluate this function. So like I said, our magnitude is 1, our frequency is 0.1. So all we're going to do is we're going to plug in our 1. So we have 1 cosine 0.1 times 1 minus 30 degrees. Now if you go plug this in your calculator, you're not going to get the right answer, because this set here is in radians, and this is in degrees. So we need to convert 1 to degrees or 1 to radians. Doesn't really matter. So I'm going to convert, and typically we'll convert this one into radians. So note that you can think of it as two ways. You could say, oh, 2 pi radians is equal to 360 degrees, so that's the full circle, or you can say that just pi radians is equal to 180 degrees. So I can take that 30 degrees and multiply it by pi over 180 degrees, cancel out my degrees, and I will get pi over 6 radians. So then I can reevaluate this as 1 cosine 0.1, so 0.1 has 1 is 1. And then don't forget our negative sign here, minus pi over 6. And when you plug that into your calculator, make sure you're in radians mode, you should get 0.9116 volts. All right. If you have any questions, feel free to contact me.